Black Hole Lab 3. The purpose of this third video lab report was analyzing the interactions coming from the surroundings into the system, starting from given data of the system's motion and positions. The system was a star while the surroundings were a black hole that interacted with the star. Since the beginning, data such as the star's mass, the star's positions, the time interval between each position given, and the constant of gravitational force were known numerical quantities. Based on these data measurements and a fundamental principle, Newton's second law, I calculated the net force acting on the star by the black hole through a computational model that used a loop to repeat a basic procedure many times. This is explained in further detail as this video goes on. Having the net force, I was able to calculate the mass of the black hole. All the results and specific measurements are given throughout the analysis of the computational model's code and throughout the discussion of this video. Let's start the analysis of the computational model that helped us to accomplish our goals stated a few minutes ago. The data we were given about the system includes the star's mass, which is 1.9890 times 10 to the 30, the time interval between each position data, which is 1 Earth day or 86,400 seconds, and of course the different positions of the star throughout the time, which won't be stated one by one. Now, the numerical quantities we have about the surroundings or the black hole include its position, which is the vector 1 times 10 to the 10, 3 times 10 to the 10, and 0. After the computational model runs, the black hole's mass is calculated. Before getting into the actual code, let's discuss the physics involved in the lab. It is known from the fundamental principle Newton's second law that F net is equal to the change in momentum delta P over delta T. They're not the same thing though, because F net represents the sum of the forces acting on the system, and these forces cause a change in the momentum of the system that equals the sum of such forces. Now, we're able to get the change in momentum or the change in time to later get the sum of the forces acting on the system. The data we have are the different positions of the system and the time intervals, right? From that, we can get the velocity at each position from the formula r1 minus r0 all over delta t. We could do the same thing for the next position and then get the next velocity. From those two velocities, we can get the change in velocity. We know that the change in momentum is equal to the mass of the system times the change in velocity, and that whole thing over delta t is equal to delta p over delta t. We would have to do this for each change in position, but the computer does that for us. Let's take a look at the actual code. Let's start with the initial conditions in our code. The first is the mass of the star, which was stated before, delta t or interval between imported data points, the time where the first observation data point, and then the CSV file has the data positions that will be read and added to a variable named IDX index. This first while loop will calculate the velocity from the data for all the positions in the CSV file. This second while loop will calculate the net force from motion data. First, it calculates the initial and final velocity from the components defined in the first loop. Then it calculates the initial and final momentum using the mass of the star times the initial velocity or the final velocity on each one. Then it calculates delta v using the subtraction of final velocity minus initial velocity, and then delta p using the subtraction of final momentum minus initial momentum. Having delta p, we can calculate dp dt just by dividing by delta t, and then dp dt is equal to the net force. These final lines of code calculate the parallel and perpendicular components of Fnet and dp dt. The arrow scale was calculated based on the positions from the CSV file. Let's run the code and see the magnitude of the net force and the movement done by the star. As you can see, the second number is the net force. In the end, I was able to calculate the mass of the black hole from the data we had. It equaled 2.38 times 10 to the 31st. We solved for the unknown knowing the net force, the constant of gravitational force g, the mass of the star, and the square of the magnitude of the displacement. Answering the second discussion question, if another black hole was acting on the star instead of the one we have right now, the movement would have to change if the black hole had a different mass because of the formula to calculate gravitational force. We will need the new movement of the star in order to calculate the mass of the new black hole. If this new movement is the same, it means that the mass of the black hole was equal to the mass of the last black hole. To conclude, it's important to say that sometimes we can start from actual data of a system's motion to get to analyze the interactions from the surroundings that caused such motion. Contrasting last labs, we started from observing the interactions and the system to predict the motion of such system. The liaison between the motion and the observation, or the other way around, is a fundamental principle. Thank you.